Today's class will start with cycle analysis. What we will do in cycle analysis is we will look at the Brayton cycle, which is mostly followed by all the air breathing propulsion systems, and look at what happens to non dimensional thrust, ISP and other parameters if you vary the Mach number. Okay, that is the primary motivation for doing this, and we will be able to derive some simple relationships and show where the optimal value of non dimensional thrust or specific impulse lies. Okay. Now firstly we will start with ramjet. As it is the simplest system with no moving parts and other things. So we will start with this, and this will be a one dimensional analysis. That is, the variation is only along the axis of the ramjet. Okay. So just to refresh, we have an intake for the ramjet, okay. This is a schematic of a ramjet. You have air coming in from the left, and you have fuel added. This portion is the intake, all this is the combustion chamber, and this is the CD nozzle. Now let me call points, let me indicate points here. I will call this 0, I will call this 2, 3 and 4. Okay. Now correspondingly I will put this information on a TS diagram as to what happens to the cycle on a TS diagram. Let us look at it. This is 0, 0 to 2 is compression, isentropic compression. We are assuming ideal processes here. 0 to 2 is isentropic compression, 2 to 3 is heat addition in the combustion chamber here, and 3 to 4 is expansion through the nozzle. Okay, fine. Now we had derived some time earlier the thrust equation, and we had seen that for an air breathing system the thrust is F is equal to m dot A into, I will call it in terms of the quantity here, I will indicate it by V naught, and sorry m dot A into 1 plus F V4, that is the exit velocity, minus V naught plus the pressure thrust A4 into P4 minus P naught. Okay. So, this is the exit velocity, this is the entry velocity, and this is the pressure thrust. Typically the pressure thrust part is very small compared to the convective flux thrust. So, in this analysis we will neglect this part. Okay. So, we will consider that the nozzle is optimal, the flow in the nozzle is optimally expanded, flow. So, P4 will be equal to P naught. So, this part goes to 0, essentially we are left with only the convective flux. Okay. Now, I can rewrite this as F is equal to m dot A V naught okay, fine. Now, further I want to simplify it. What we know is that velocities are related to Mach number and speed of sound. So, I will use that information. I know V naught is equal to m naught A naught and V4 is equal to M4 into A4. I also know that A naught is nothing but and A4 is okay. So, I know the relationship between the velocity in terms of Mach number and then in terms of temperature. Now, we will make an assumption here. If you see here, A4 corresponds to the velocity of sound at condition 4. At condition 4, you realize that we have added fuel and burned the fuel, and therefore, the composition of the gases at 4 and 0 are not the same. So, typically speaking, I should have written different notations for these two, right. But in this analysis, we will assume that as the gases pass through the device, there is no change toward to either gamma or R. Okay. So, assuming R and gamma to be the same for exhaust gases and ambient air. Okay. Then we can do the further simplification of this. So, I can now write F is equal to m dot A. I know that V naught is nothing but m naught A naught M4 Now, if you remember our discussions earlier in the course, in all the air breathing propulsion we said that if kerosene is the fuel or any hydrocarbon is the fuel, then F, the fuel air ratio, that is m dot F by m dot A for stoichiometry is around 6-7. Okay. So, this is pretty much less than 1. So, we can neglect F in comparison to 1. Okay. So, F is very much less than 1. So, I can rewrite my equation as F is equal to m dot A, m naught A naught so this goes to 0. I will get m4 into here. I know that A4 is gamma RT4 and A naught is gamma RT naught. What I will do is I will take out the gamma R part because of this assumption, and I will be left with m4 by m naught into under root okay. So, we have been able to express this in terms of ratio of exit to inlet conditions. Now, what we will do is what is known as cascading of pressures and temperatures. We will try to cascade from the nozzle side towards the inlet and see what we can get out of this. We will do cascading of pressures and temperatures and see what we can get out of it. Firstly, let me take T4 by T naught. T4 by T naught, I can write it as T4 by TT4 into TT4 by TT3 into TT3 by TT2 into TT2 by T naught, or I will call this TT naught to TT naught by T naught. The subscript T here indicates total. Okay. So, total or stagnation conditions. Okay. So, what we have done is we have expressed it as a ratio of static to stagnation, and then stagnation of 4 to 3, 3 to 2, 2 to 0, and then stagnation to static. Okay. So, all these will cancel out and you will get T4 by T naught. So, let us look at what are these values. This is nothing but local static to stagnation condition, which we can express in terms of Mach number. This, what does this represent? Tt4 by Tt3 is this by this, it represents flow through the nozzle. Similarly, Tt3 by Tt2, 3 and 2, it represents flow through the combustor. This represents flow through diffuser or intake, and this again is local static to stagnation. Okay. Now, for an isentropic flow, what happens to this ratio Tt3 by Tt4? If we assume the flow through the nozzle to be isentropic, then both these temperatures are same. So, you get this ratio to be 1. Okay. Then again flow through intake, this is also 1, fine. You are left with now 3 things: this flow through combustor and local static to stagnation. This, the first and the last one, we can express it in terms of Mach number. Okay. We will do that right now. So, this would be 1 by 1 plus gamma minus 1 by 2 m4 square, okay, into 1, and again this would be one plus gamma minus 1 by 2 m naught square. Okay. So, lastly we are left with flow through the combustor. Now, let me call this ratio Tt3 by Tt2 as I will call it tau b. Okay. Now, I can also express that this tau b as Tt3 by T naught into fine T naught cancels out, you get the same thing. This is equal to T naught by okay, T naught by Tt2, this is flow through the intake which is 1. Okay. So, this is 1. So, you get this we can express in terms of Mach number, okay, and let me call Tt naught by T naught as theta naught. Okay. So, if I call T T naught by T naught as theta naught, I will get tau b as equal to T T 3 by T naught into 1 by theta naught. I will also call this quantity, I will define T T 3 by T naught as theta b. This is nothing but the ratio of the exit temperature of the combustor to the ambient temperature. Okay. Now, this is under the designer's control, right. So, therefore, this is a very important parameter, as we will see later on in the discussions. So, T T 3 is temperature at the exit of the combustor and T naught is the inlet temperature. Okay. So, we will call this theta b. So, I get tau b as, this is nothing but theta b by theta naught. Okay. So, if I substitute back for this T 4 by T naught, all this, I will get the following expression. Let me put that as 1 by 1 plus gamma minus 1 by 2 m 4 square to 1 into, if you see here T T 3 by T T 2 is nothing but tau b, which is nothing but theta b by theta naught. Into flow through intake, which is 1, into the last part 1 plus gamma minus 1 by m naught square. I have defined this ratio as theta naught here. Okay. So, I will put that down. So, finally, we get T 4 by T naught is equal to theta b by 1 plus gamma minus 1 by 2 m 4 square. Okay. Now, we have been able to derive this expression for T 4 by T naught by cascading temperatures. Let us now do the same exercise by cascading pressures, try and find out what is the relationship for Mach numbers. Okay. So, similarly, we get P 4 by P T 4, P T 4 by P T 3, P T 3 by P T 2, P T 2 by P T naught into P T naught by P naught. Okay. Again, T indicates, the subscript T here indicates total conditions or stagnation conditions. So, this is a ratio of pressures static to stagnation. The first and the last terms are ratio of local static to stagnation pressure, one is at the exit, one is at the inlet. Okay. Now, this is flow through diffuser, flow through combustor and flow through intake, right. Now, this pressure term here, the pressure term here, this indicates the efficiency across the nozzle. Okay. This indicates the efficiency across the combustor and this indicates the efficiency across the intake. So, I will call them as, this is nozzle efficiency eta n, this is burner efficiency B eta B, and lastly this is diffuser efficiency eta D. Okay. The other two terms can be expressed in terms of Mach number. Okay. So, we get P4 by P naught is equal to 1 by 1 plus gamma minus 1 by 2 m4 square gamma by gamma minus 1 into eta n into eta b into eta diffuser or intake into 1 by gamma minus 1 by 2 okay. So, this is the expression that we have. What is P4 by P naught? Remember, when we started out we made an assumption saying that P4 by P naught is equal to 1, optimally expanded flow. So, P4 by P naught is okay. So, you get 1 plus gamma minus 1 by 2 m4 square okay. This is the expression that we get by cross multiplying. Now, I will put all these three ratios into one value of eta and I will express, let us say eta is equal to eta n into eta b into eta d to the power of gamma minus 1 by gamma. If I do it this way, then when I plug in for this, it will all be a relation of gamma by gamma minus 1. So, I can remove the powers and look at what we have here. Okay. So, we get finally 1 plus gamma minus 1 by 2 M4 square must be equal to eta into okay. The powers get cancelled out. So, you are left with this equation. Just to remind you, we had done this exercise earlier, the relative values of all these efficiencies. Eta n typically its flow through the nozzle, it varies between 0.96 to 0.98 and eta burner, this varies between 94 to 96 and diffuser remember we had indicated this to be a strong function of inlet Mach number. If you have a large inlet Mach number, you are bound to get lower efficiency because of flow being processed through oblique or normal shocks. Okay. So, you will get a lower efficiency if you have high Mach number, but as you go down in Mach number you will get a higher efficiency. So, if you combine the worst case scenario of all this, and remember that it is a multiplication sign, you will end up getting variation eta varies from 0.84 to 0.97 for gamma equal to 1.4. Okay. So, the worst case scenario is this 0.84 and the best is 0.97. We will discuss about this when we talk about what is the lowest Mach number in which a ramjet can operate. Now, coming back to this equation here, this was our relationship that we were trying to find in terms of Mach numbers. What is this term here? This is nothing but theta naught, right. So, we get 1 plus gamma minus 1 by 2 m naught square is nothing but theta naught. So, from here you get m naught is equal to 2 by gamma minus 1 theta naught minus 1, and similarly if you put this theta naught here, you can get an expression for M4 as okay. So, now we have the relationship for M4 by M naught and T4 by T naught. In our earlier thrust relationship, we were searching for a relationship for T4 by T naught and M4 by M naught. We have got both of them. Let us plug it in and see what happens. So, our relationship M4 by M naught is equal to eta theta naught minus 1 divided by theta naught minus 1, and similarly T4 by T naught was theta b to 1 plus okay. What is this term? This is nothing but this term here, right. So, it is nothing but theta naught. So, you get theta b is equal to T4 by T naught is equal to theta b by eta theta naught. Okay. This is because we have shown that 1 plus gamma minus 1 by 2 m4 square is nothing but eta theta naught. So, we have both the ratios that we were looking for. So, our thrust equation becomes F is equal to m dot a naught m naught we had m4 by m naught, that is nothing but theta b. I will firstly put T4 by T naught eta theta naught into okay. This is the expression that we get for thrust in a ramjet. Okay. Now, we like to have non-dimensional numbers. Okay. We can easily see that we can non-dimensionalize this thrust if we divide by m dot a naught throughout. Okay. Mach number is not a function of I mean it is a non-dimensional value, and all the other things theta b, eta and theta naught are also non-dimensional values. Okay. So, I get F by so this is the expression for non-dimensional thrust okay. Now, we have found out what is the expression for non-dimensional thrust in terms of theta b, which is nothing but the ratio of combustor exit temperature to ambient temperature and a function of Mach number and efficiencies. Okay. Theta naught is a function of Mach number and eta is efficiency, and m naught is again Mach number itself. So, the only input parameter that we have under our control is through theta b and the flight Mach number. Okay. The rest of it is system determined, that is theta or the efficiency is system determined. Okay. Now, we have been able to do this. We also need another parameter, right. What is the other parameter of interest to us? Specific fuel consumption. In this case, we look at ISP, which is 1 over specific fuel consumption. this is nothing but specific impulse and it is 1 over SFC. We define ISP as ISP is nothing but thrust per unit mass flow rate of fuel. Okay. So, what we have got is an expression for F by m dot A, and now I have a definition for ISP like this. Fine. What we have to look at is, we have spent a considerable effort trying to derive that expression. We have to take a little more benefit out of it. So, what we will do is we will multiply this suitably and find out if we can use that expression. Okay. So, I can write this as F by m dot A into A naught into A naught divided by F, where F is nothing but fuel air ratio m dot F by m dot A. So, if you put m dot F by m dot A here, this m dot A and this m dot A cancels out, and A naught and A naught cancel out, you get F by m dot F. So, we have been able to get this expression that we have derived here. Okay. So, if we want ISP now, the only parameter that we need to derive an expression for is this F here, right. Okay, fine. We will do that right now. We will derive an expression for F by looking at the energy balance across the combustor. Okay. So, using energy balance across combustor, that is, what you are putting in is chemical energy associated with the fuel, that is given by m dot F, that which is the mass flow rate of fuel into the calorific value of the fuel. Okay. Q indicates this must be, what must this be equal to, the sensible enthalpy rise across the combustor. Okay. So, that is given by m dot A into the 1 plus F here indicates that you are looking at the combined mass flow rate of fuel and air when you are looking at conditions at 3. Okay. Now, again using our, this is a little weird, you are trying to get an expression for F, and what we are trying to do is we will try and see if we can eliminate this. Just to make sure that our algebra is a little more cleaner, we will do this. F, you can compare it with 1, always in engineering approximations you tend to compare it with a known value, and then if it is very small compared to that value you can neglect it. Okay. So, you cannot neglect it arbitrarily, but you have to make a comparison with some other quantity. So, if you compare F with respect to 1, we have seen that F is very much smaller to 1. So, you can neglect this part here. Okay. So, this goes out, we get m dot F Q is equal to Cp is common for both the burnt gases as well as the incoming air. So, I can take it out. Okay. Now, I need to let me divide both these by T naught. Okay. So, I can write this as m dot A Cp T naught right. I have divided and multiplied by T naught. So, what is T T3 by T naught? When we derived expression for F by m dot A, what is this expression? This is nothing but theta b, right, and what is this? Tt2 by T naught is nothing but Tt2 by Tt naught into Tt naught by T naught, right. What is this ratio? This is flow through intake, this is 1, and this is, what is this? Theta naught. So, you get, if you substitute back in here, you will get m dot A Cp T naught into theta b minus theta naught. So, finally, we can get an expression for F by combining these two. We can write F is equal to Cp T naught by Q into theta b minus theta naught, and therefore, our expression for ISP, you see here this expression for ISP that I have, if I divide the ISP by A naught, I get a non-dimensional quantity. What is the unit of ISP? ISP is, unit is what? Newton per kg second, right. What is Newton? Newton is kg meter per second square, you get kg by per second. So, what you will get is meter per second. Okay. So, if you split it, if you simplify further, you will get ISP unit as meter per second. A naught is nothing but speed of sound, which is also in meters per second. So, you will get a non-dimensional quantity if you divide it by A naught. Okay. And if we substitute the expression that we derived for F by m dot A naught, we will get this as eta b eta theta naught into theta naught minus 1 this is the expression for ISP by A naught. Okay. We will stop here, we will continue in the next class. Thank you.